object storage debate, and it's really after the last two OpenStack events, storage has been at the heart of the discussions in both of those summits, and more importantly is about what storage is right for me, block, object. So some people are using objects, some people are using block for different applications and different requirements. I'm going to hand it over to William, who is our CEO, and he's going to talk us through the webinar session. Thank you. If you have any questions, please just put them in the chat, and we'll answer the questions at the end. Thank you. And William is traveling, so excuse the noises if you hear any noises. Go ahead, William.
Good afternoon, everybody. So, as Mo said, really from our OpenStack experiences in Paris and before that in the USA in Atlanta, quite a lot of people have quite a lot of questions around the practicalities of object, block, file systems, and how do they all play together in the data center? Are they exclusive, and what are their merits and strengths? So this is really just a contribution to the debate. We're not trying to say that there's any one particular answer. This is our contribution to the debate. So if we just roll on to the first slide there, within the data center, you have to imagine what are the storage requirements within the data center. And there's a lot of requirements. You would wonder how any one particular technology can fulfill all of those requirements. But what they really all, if you break down each of those lines, you can see that there are some things that we'd expect. So first of all, that there's a wide range of application workloads that exist in the data center. Not everything is a video download or a workload that's specifically tailored or works well with object storage. There's lots of transactional type workloads and lots of workloads in between. So there's a wide range of workloads in the data center. And whatever storage technologies you use, they should be appropriate to handling that workload. There is also within the data center, lots of different consumers. So there's not just provisioning of virtual machines, but there's entire tenant spaces that need to be provisioned. There's storage-centric services within the data center itself, and there are various IT nodes that need to be provisioned. So again, there's a wide range of consumer types that we can identify in the data center. And of course, profitability is going to be driven around concerns of OPEX and CAPEX. So whatever technologies we use, they have to be able to provide and provision that storage at an OPEX that's appropriate for utility cloud type pricing. And this is one of the areas where people perceive object storage as having a big success. It's low OPEX because it's quite frequently open source software. CAPEX as well, another requirement is that today the whole utility cloud and increasingly data centers are being driven to x86 platforms for everything, for their compute, their storage and networking. So hyperconverged systems are extremely important in this area. So CAPEX is best achieved by using standard open platforms. In addition to those, the issues of provisioning, OPEX, CAPEX, there's no point in data centers having services unless they're highly available and very resilient. So availability and resiliency, again, are key issues that storage has to deliver on the data center. As services and subscribers grow, then scalability is a very important issue. And object storage has a very good story in terms of the scalability, and as we said, performance per workload type. So if we move on to they're the storage requirements in data centers that we're trying to address. And actually, one last point before we leave that there, if we just go back to the previous slide. It should be remembered it should be remembered that there are many very many fabrics that exist in data centers that are high performance fabrics for different workloads types. And not all of those fabrics will support something like object storage. And in particular, if we think of fiber channel, that is a fabric that has very good performance characteristics, but it may not be appropriate for doing object storage workloads. Well, perhaps on the storage node side. So if we move on to the next slide. So if we break those all those requirements down, we find that there are 6 big issues: resiliency, scalability, application workloads, provisioning to all the different consumer types, the CapEx and OpEx issue, and storage has to be secure. So this webinar is going to look at those big six issues and see where object storage and block storage fulfill that need and how well they do it and where the gaps are. So if we go to the next slide. So they're the big 6 issues. If we move on, Mo. So there's a long scientific way of ranking those different technologies, and MPSTOR has done its own ranking, and the way we would rank those technologies in terms of those big 6 issues out of 10, you can see that block storage in some of those ways has a higher score compared to object storage. There may be, it may be maybe not a fully objective way, but it's and there is some subjectivity in it. But I think largely the industry would agree that on resiliency, block storage, which is a very mature technology, has many different frameworks and methodologies for achieving real-time consistency of data, is a more resilient framework than object storage, which relies on deferred in time copies of data. So we can say that block storage on a number of measures outperforms object storage in terms of resiliency. In terms of diverse workloads, we'll have a little look later on that the whole semantics of object storage don't lend themselves to transactional type operations. So for very wide diverse workloads, block storage does have a better story and a better ranking. In terms of the total cost of ownership, object storage is open source software. It will run on pretty standard hardware and commodity type storage media. So I think all in all it probably has a better score than block storage, especially if that block storage is coming from a proprietary vendor where the block storage costs can become very, very high very, very quickly. In terms of storage security, neither framework is really has much of an advantage over the other. And in terms of scalability, object storage today is perceived as having a better scalability characteristics. And I think that's quite true, but there are new technologies, and there are certainly technologies which help block storage to scale out, and we'll have a look at that a little later. And finally then, the whole area of multiple consumers. Block storage is a lower level type of storage, so therefore, as being a more basic type of storage, it's easier to provision a wider range of consumer types. And by consumer types, I mean just consumers of storage in the data center, then enforcing that all of those consumers use use an object API. So if we look at the next slide, we can see that all of our not one paradigm does not fit all. So if we look at block has some advantages. If we look at object, it has advantages. Our graph is a little bit messed up, but I'm sure it's understandable. And then the question mark is there something in between block and object, or an extension of block and object, or is there something that can actually give us what we want on every single on every single storage issue that we have in the data center. So if you look, as we said, from a resiliency viewpoint, object suffers from a disadvantage that the data consistency is not consistent immediately. It does require deferred copies made to the object store over time. So there are serious windows here where data could be lost in the case of failures. The diverse workloads, we already mentioned that there's a narrow range of workload types that works for object. Block storage, there's a very high cost to administer block storage. Block storage is a system administrator type storage. Without a software-defined storage framework, of course, it's very much driven by a system administrator, whereas object storage has the advantage of being has an API that the end user application can use to provision storage for itself. In terms of storage security, neither framework really works well, and scalability, the block storage can be very, very difficult to manage at scale over multiple fabrics and multiple tiers of storage. And for the multiple consumer types, there's probably a missing paradigm that's missing both in block file and object storage. So if we run on to the next slide. So to recap, object storage is resilient to component failures because multiple copies are kept. It's scalable and it can be delivered on open hardware platforms. And it is definitely cost effective for some workloads type. Its strong point is cost, scalability, and managing the impact of disk failures because of the fact that you can set up an object store with multiple copies. But object storage has poor performance in workloads requiring high I/O and low latency. So it can deliver partially on those big 6 issues. Block storage is resilient and a somewhat less scalable technology that is usually delivered on proprietary platforms, but it does support all workload types. So block storage that is available on open platform can help mitigate against that difficulty. But block storage strong point is it's very good mixed loads workload performance. It has support for different media types and fabrics, but scaling can be difficult, and the recovery time from failures can be large when they have large silos, due to the fact that recovery requires usually building some sort of parity for information that's been lost on the disk. So once again, it can deliver partially on the big 6 issues. In the following slides, there's quite a lot of detail on the merits of object storage and block storage. We have about 10 slides here which go into the details of how we came up with those numbers for how good or how bad object storage is with respect to block storage. So I think that this is the type of information that probably can be read offline. I'm certainly not going to go through all of these slides one by one. So I think we can skip past the detail here of how all of these issues are resolved either using block or object storage. We'll just keep on skipping down. And for those people who are interested, they can read this offline. So should we use block, object, both, or something else? Is at the end of the debate that just object storage has its merits, block has its defects, and vice versa? Do we need both? Is there something else? And what are those hard limitations? So we'd like to throw a little bit of light and some comments on those questions. So if we move down to the next slide. So where do some of those limitations come from, or where do some of those performance hits come from? Well, the first thing to remember is that, block versus object semantics, that the semantics of using an object store are very, very different from using block storage. Block storage is a very elemental type of storage upon which, in fact, object stores are built. And quite simply, to access a storage volume, all you need to throw at it is a SCSI command, the SCSI CDB, with an LBS, that's an offset within the volume, on a 512 byte boundary or a 4K boundary, and the length of data that you want. So the semantics of accessing and manipulating block storage are very, very, very simple. They're very, very fast. Accessing anywhere within a volume is nothing more for the device to do a lookup based on the logical block address. But if you look at an object store is itself a complex application which uses databases and metadata, has an API head, and the semantics look completely different to a SCSI command. So those semantics lend themselves to doing certain things. With the object store semantics, one can indeed actually build a block device on top of object store semantics. However, it's very cumbersome and has very many performance issues because of the large number of steps that you need to translate between giving a block address and then mapping that to an object store. So an object store semantics are completely different from block, and they're at a much higher level, and they require the object application itself to use things like databases, to use file systems, and all of these higher level constructs all sit on top of a block device. So using object storage requires an awful lot a lot of additional overhead than just accessing a block device. So if we look at the next slide, we can see that at layer 1, a block layer, your standard hard disk driver is sitting very, very close to a disk. The coupling is very, very high, and the taking any low-level SCSI command and translating that into a disk access and returning the data is a very efficient operating system. And then on top of that, if we move up this stack, we can see that we have to put a file system, which adds additional overhead, and then a whole object layer management function for doing things like copies and maintaining the consistency of the object store. In addition, then, we need databases and all of the files that are associated with the objects, and finally an API head, which replaces the function of the SCSI block layer. So just by looking at this simple stack, we can see that going from a block layer interface all the way up to an object layer interface, there's a lot of additional overhead. Even if you use an object layer, an object store, there's still a requirement within the data center to have block layer access, and there are tools such as S3 Backer, and there's quite a number of S3 tools to map object stores to block devices, or to use Red Hat's Inktank product, the RDB, the Rados block device, which can map a block device all the way down to an object. But again, if we access or create a block device at that point 3, we have quite a lot of overhead, much more overhead than if we just directly attacked our interface with the block device at layer number 1. So the first point is the semantics of block object or block over object. The semantics are that accessing a low-level block device is always going to be much faster than accessing over an object store. Now, that is absolutely true, but in a good many cases, or in some use cases, that overhead may be insignificant. And particularly in the case of streaming data, where the objects or the files or the files sitting on a block could be quite large. So in streaming data, the actual penalty or the setup overhead might actually be so trivial compared to the time to download or stream a very large file that it may not matter. So in some cases, whilst this may be absolutely true, it may be quite irrelevant. But where it's not irrelevant is when you have lots of transactions. So a good many workloads require random type and lots of I/O operations. In those cases, the block layer solution is going to provide better results. And if we look at the next graph, next slide, this is from MPSTOR's labs, but we have external proof points which also show this to be true, and we have customers who have also done independently these type of tests. And what they show is that if you look at CPU utilization and if you look at IOs per second, you see two things. One, you see that object storage quickly saturates a machine at a far lower IOs per second than if you're doing it at block. And 50K IOs at 8K is a data point that we've measured and validated using HDD technology in sequential, and you still get the same number if you run random on solid state disk. But you can see there's quite a difference. It's about six times more powerful, or 6 times better results on block over object. So these particular tests here were done, or these tests here represent 24 solid state disks on a high-end multi-core x86 machine over 40 gig Ethernet using ISER or DMA type technology. And still block will significantly outperform object in IOs per second. So if we move down to the next slide. So if we leave storage and just move on to the next issue, which is of concern within the data center, which is the whole area of scale-out storage. This configuration here shows a number of proxy nodes back-ended by a large number of storage nodes. And this would be the typical, apart from not showing load balancers here, but this would be a typical configuration that would be set up in order to build an object store. All of the cluster nodes would be running, would run an object proxy, and all of the nodes 1 to 128, for example, would contain the storage nodes. However, as we said earlier on, that this may not look typically like a block storage solution. However, there are technologies, scale-out block storage technologies, which can manage this type of configuration as effectively and as easily as setting up an object store. So one of the responses, I think, of block storage to the object storage scale-out capability is block storage scale-out. And block storage scale out is simply a way of replacing an object proxy with a block proxy, and that block proxy can build storage volumes over a very large and scaled out back-end storage. In itself, there is no Ceph equivalent or Swift equivalent of scale out block storage. It is a difficult and complex technology to get right. There are commercial products such as EMC's Scale.io type products. There are others. MPSTOR has a scale out block storage solution. But I think it's worth noting that the pools of sound storage is not the only option that you have when you go to get high performance on block storage. That there are scale out block storage technologies. So if we roll on, we'll have a little just a quick contrast of exactly or some insight into what we believe this scale out issue is and how scale out can help in block storage. So what we mean by scale out is that a storage service can scale in real time without service interruption, and both the capacity and the performance can scale. So by that definition, we can see that there are some solutions in the block area, such as Scale.io, such as MPSTOR's information dispersal technology. Object storage, Ceph and Swift would fall into this, and indeed some of the file, GPFS and Gluster would fall into this area of a scale-out storage service. So if we move on to the next slide. So I think this type of diagram would be quite familiar to most people who built object stores. An I/O intercepted by a load balancer, and that load balancer feeding or redirecting that to whatever proxy is available, and each proxy has access to all of the storage arrays in its object ring, and then writing that data to one of the zones, and then additional copies then being written to other zones within the ring. And this is a standard classic object storage organization, and the merit and the value of this is that we can keep adding in new storage arrays, adding them into zones, or indeed incrementing the number of zones. And as we do that, we add either more proxies or we add more storage arrays, and the service can scale out. If we look at the next slide, in a very analogous way, we can use scale-out technologies. These scale-out technologies using information dispersal are analogous to an object storage. However, I can't point you to any open source scale-out block storage solution that's open source. These tend to be proprietary products, but some of them will have price points that in a scaled out object storage will be pretty much equivalent to what an object store. If you imagine a large object store, the predominant costs are going to be in the storage media and in the storage servers. So your CapEx costs are going to be quite considerable. The additional overhead of proprietary software, when it gets down into the dollars per, or even tens of dollars per terabyte, can become quite insignificant, even if it is proprietary storage software. And certainly when you start adding in support for both types of solutions, block scale-out storage does have OpEx and CapEx costs which come very, very close and pretty much align with object storage, CapEx and OpEx costs. But in this block IDA scheme, data written to this higher level interface, this virtual block store interface, gets written across in pretty much an analogous way different storage arrays within its storage group, and parity information is then added to the end of that write. And this type of scenario gives you the exact same resiliency. It has the advantage of the data is all written consistently within a single time, a unit time period, so all the data is written at the same time. Any particular storage array dies, there's enough parity in the system to recover, and the storage efficiency is much higher because we're not using multiple copies. We're only writing the stripe using an information dispersal algorithm plus an erasure code across all of the arrays. So if we go to the next slide, when you compare and contrast both of these methodologies, object storage is going to make copies, but there's a large window of non-protection in time across multiple storage arrays. And scale-out block storage will store data redundantly in real time across multiple storage arrays. So one has a strong real-time consistent data, and the other one, object storage, has a weak real-time consistent data. And this can be a problem if the copy time within your object store becomes quite long, and that will happen in large arrays. If we move on to the next slide, at the lowest level, the way a scale-out block level device is going to work is pretty analogous to how it's going to work in an object storage, except that your lowest level, your unit is a range of block addresses as distinct from multiple copies of different objects. And instead of using multiple copies in a block storage, you're just going to write your data across, you're going to stripe it across multiple arrays and tag onto it enough erasure coded parity information so that you can recover your data if any storage array dies. Also, you're probably going to build your volumes across different RAID groups, and those RAID groups can be at different QoSs to give you volumes which will perform depending on what type of media they've been built on. So if we move on to the next slide, scale out. I think we need to down tab a few there times more. If we look at scale out, scale out is not managed pools. So if we look at frameworks such as EMC Viper, or if we look at OpenStack's Cinder and the various plugins, these type of frameworks, these software-defined frameworks, are very good for managing different pools of data, and those pools of data can indeed be provisioned with whoever does the plugin. Certainly MPSTOR's OpenStack plugin will manage multiple different types of fabrics, multiple tiers, etc. But that in itself is just managing lots of pools of storage over multiple fabrics with different media types. That is not scale-out storage as such. Scale-out storage is the definition that we've used earlier on. And again, EMC's Scale.io software or MPSTOR's Orchestra IDA type technologies are examples that map closely and use the same paradigms as Ceph or Swift. So we're not saying that managing lots of pools is a scale-out solution. It really is just an automated management of lots of pools of storage. Scale-out storage, block storage is different. If we move on to the next slide, So if we look at another aspect of block versus object storage, the efficiencies that you achieve with block and object storage are again quite different. And because object storage requires multiple copies, the efficiencies can drop quite considerably depending on how much the number of copies you want to keep. Whereas using an erasure code of 1, 2, or 3 will give you similar, not exactly the same, but it still gives you a very high level of redundancy and resiliency in your system while still achieving a very high storage efficiency. So block and object storage efficiencies are different even with similar redundancy in the system. Now, what this graph doesn't show here is the impact of losing a storage device or the impact of losing a storage array. The recovery times for object storage is a lot faster than the recovery time for block storage. So there's never, there's always a gain or a loss. So the recovery time from, or the impact of a failure, the loss of a storage array or the loss of a block device, does have a much higher recovery time in a block configuration than it does in an object configuration. So if we move on to the next slide. So I've just added this slide in here because I think it's an important point to note that in data centers, multi-tenancy is a very important issue. So when you're trying to offer storage to a user and who's prepared to pay for a certain SLA, then really what you want to do is you want to you don't want some tenants to get too much bandwidth or too little bandwidth. You really want them all to stay within an SLA range. And the whole issue of throttling, both on IOs per second or in bandwidth, is from a practical viewpoint, MPSTOR runs its own cloud, so we see practically when the inventory of volumes gets very large and the number of subscribers increase, we see that making sure that people stay within their SLA is very important. It is intrinsically a lot easier to put the type of control mechanisms and the control loops around block storage in place than it is around object storage. It is an easier task to do. So it should be a consideration of how to enforce a policy of the maintaining your IOs per second in a multi-tenancy cloud, how that is done either with your block or object storage. It seems to be an easier task to achieve with block storage than it is with object storage. We're getting near the end of the webinar, so we're going to try and wrap up here now in the next couple of slides. So if we move on to the next slide, another point to consider is that within the data center there are lots of features that need to be implemented for very good reasons. Thin provisioning is an example of a feature which is demanded. Snapshots, rate limiting, replication, tiered storage management, etc. So there's a whole set of different types of storage features that need to be available either to administrators or to end users of storage. And not all of those features are not always available in an object storage solution, whereas they're kind of de facto standards in a block storage solution. We move to the next one more. So what are all these different storage categories and contenders then for how are we going to solve all of our storage needs? And today, if you trawl through the the literature, you'll see a lot of names like software-defined storage and converged storage, server SAM, block file object, vSAN, etc. And a lot of those terms can be confusing, and in some cases they're not solutions in themselves, but they're just part of a Mo? Hello?
We're here, yeah.
Okay. They're just part of a wider storage solution. So if we move on to the last slide there, Mo, the next slide. So I think what we've seen in this webinar is that, you know, one paradigm does not fit all. That if we look down to the issues in the data center of resiliency, different workload, TCO, both on CapEx and OpEx, storage security, scalability, and provisioning of all of the different multiple consumer types within the data center, that there isn't a solution to all of them. However, what we can say is that if your need is for, depending on your need on whether it's strong or weak real-time consistency of data, you may choose block or object. For a diverse workload range, you definitely need to consider block performance, because the block performance is going to be far superior. In terms of the TCO, if you can use standard hardware platforms for block or object and use software-defined storage technologies to automate all of your block provisioning processes, then you can indeed stay within the TCO, CapEx and OpEx requirements compatible with utility cloud. So software-defined storage is a technology which helps reduce the impact of the very high and complex overhead of block storage. In terms of storage security, I think that neither technology addresses all the gaps, and there are gaps that do exist. And scalability, whilst object storage has built into it the concept of scalability, object storage has built into it the concept of scalability. Block storage can scale if on top of the block storage you use a scale-out technology. And when you look at the scale-out technologies that are available in the once the storage silo becomes large, the cost of a proprietary scale-out solution may be insignificant compared to the overall CapEx cost of the storage itself. And multiple consumer types, I think neither technologies fully address all of the different data consumer types within the data center. So I hope that webinar gave some food for thought or contributed to the block versus object debate. I hope we've tried to stay objective and informative, and have not championed one over the other, one technology over the other. Back to you, Mo.
William, thank you very much. That was really insightful, and it gives a clear view of what the differences are, and it answers some of those questions that we talked about at the different OpenStack summits. I have a few questions. I have a couple of questions myself, but I have a few questions here. One of them, the first one is about Ceph. I get block with Ceph. How is this not a block? So when we talk about a Ceph as being a block storage, how is Ceph not a block?
Well, if we go back and look at the, I think it's slide number 6 or 7, we can see that Ceph is fundamentally an object store. On top of that object store, there is a RDB device, the Rados block device. That's right there, number 21. So the block interface in Ceph is through that RDB device, and that RDB device itself is sitting on top of an object store, which itself is sitting on top of a block device. So yes, it's correct that Ceph will give you a block device. However, it's still going through an object storage and incurs all of the overhead that entails. So, you know, the semantics of block over object on top of file system on top of block is far less efficient than simply taking a block volume, terminating it in a nice SCSI initiator and presenting that to your consumer.
Okay, thank you. So it's a block on top of an object on top of a block, and the limitation of performance. You won't get the same performance as you would get from native block. Correct?
Correct. Yeah. So you actually see that when you look at the performance metrics that block semantics are just far superior, far faster than block over object over file system over a block device.
Okay, so I have just around this question, William, of Ceph. So just trying to explain it in terms not as technical as what we use. So Ceph is a block on top of an object on top of a block. So the first block underneath is the disk. On top of that there is a file system, and on top of that there is management to make the object. And then on top of that object there is a whole block again built, which is the Rados block device. Okay, that's how Ceph works.
So Ceph can operate in two modes. One, you can operate it with just a standard S3 object store interface or an object interface. That's, you know, the simplest way to use Ceph storage. Another way to use it is on a node which needs block storage, is to put a driver called the RDB, the Rados block device driver. That driver won't talk directly to a disk. It actually talks to an object store which is sitting on top of a file system which is sitting on top of block storage. So all of that overhead and doing all of those translations between you know, through the RDB driver all the way through the object store, etc., adds huge overhead, and that overhead translates into a large reduction in performance.
Yeah. Okay. So I think that's explains a little bit more. So just on that point, so you've got Swift, which is an object storage. You've got just to recap on the Ceph. So you've got Swift, which is an object storage, which is an object built on top of hard drives. You've got Ceph, which can act either in a native object storage mode or in a block storage mode by putting the Rados driver on top of it to make it look like a block device, and then exporting that through a nice SCSI interface. And then you've got block storage, which everybody is familiar with, which allows you to take a disk, create it into a RAID or some kind of erasure coding mechanism, and then export that, build a volume or a pool on top of that you can export to either SCSI, SIP, NFS, SAS, fiber channel, and InfiniBand. Okay, so that's just to recap on the objects and the definition between object, block, and the differences between block and Ceph. Okay. Another question here, and please keep your questions coming. We've got another 7 minutes. IDA, is this the same as RAID? If not, how is it different from RAID? And there's another question, is this an MPSTOR specific technology?
No, so IDA is an acronym for Information Dispersal Algorithms, and information dispersal isn't the only, information dispersal can be used both with block or object. So information dispersal really means how to take your information and disperse it in an efficient way that will give you some benefit across different storage nodes. And a storage node can be imagined as just being one huge disk, if one wants to imagine it that way. So information dispersal tries to map your IOs and split your IOs up over a large number of storage nodes. And by doing that, you bring into operation a larger number of arrays when you're doing IOs. So at any one time, you will find statistically all of your storage nodes are actually doing work. So information dispersal is designed to make sure that all of your storage arrays and all of the underlying storage, be it RAIDs or disks, are all being used. So it maximizes the parallelism required for IOs to take place at high IO rate. Like RAID, when it writes at IOs, it uses an erasure. It uses erasure code techniques to write additional parity. And when that parity is written, it maintains metadata about the volume, the IDA volume, that allows it to recover the original data in the same way that RAID would be used if a storage array was to fail. So there are similarities, but it's not exactly the same.
Okay, very good, William. Thank you very much. One last question. You mentioned Viper. How does your technology differ from it?
So, EMC's Viper is an evolving product. At the moment, it provisions storage from an object store, from the EMC Atmos store. MPSTOR can provision not just object store, but also block storage. And the provisioning in Viper is the client in EMC Viper. Whilst it can be physical nodes, it's primarily intended to be used with VMware. Whereas MPSTOR can provision not just it's a framework for provisioning not only virtual machines, but the SDS framework can also be used to provision a scaled-out block or object store. So there are additional frameworks. It's a more comprehensive set of tools for managing in a more global way all of the use case requirements within the data center than the EMC Viper product.
Okay, William, I think that's all we have time for. As I said, we're recording this session, so if anybody has questions after the session, please don't hesitate to send them to mo@mpstore.com, and we will answer your questions. We'll make also available the webinar session online, so you can, if you didn't get a chance to join us, you can look at it at a later stage. Thank you very much, and thank you, William.
Take care.